Hello, we'll do now Unit 3 for chapter number 4, stoichiometry. This particular unit is based on the solution chemistry so that also becomes a part of stoichiometry. And before we start this particular solution chemistry, there are some items that you must know. But in terms of definitions, so solution chemistry, what are the terms? What are the units? The calculation of moles or grams of solute or volume of solvent, preparation of a solution, dilution of a solution. Now, with that, I'm going to start showing you some important definitions and information that you need to know. Most chemical studies require quantitative measurements. Experiments involving aqueous solutions are measured in volumes of solutions rather than masses of solids, liquids, or gases. Solution concentration is expressed as molarity, and it is defined as the moles of substance divided by the volume of the solution in liters. From that particular experiment, because when we talk about molarity, the qualitative aspect is that we are saying whether the solution is very strong or very weak. And quantitative is it is able to tell us the amount of solute and solvent in a solution, mass percentage that we have already covered, and molarity, key to stoichiometric solutions that are there. So mass percentage will be covered in chapter 13, though we did a little bit of it at the beginning of this chapter under stoichiometry. Now, solute is the amount of solid or liquid or gas that is dissolved in a given solvent. The solvent is always present in a much larger, greater quantity as compared to the solute, because depending upon the volume of the solvent, you can have the different types of solutions. And so here, when a solute is dissolved, the lesser one with the solvent, for example, copper sulfate, you can see how nicely the solution gets dissolved. And when we dissolve it, you see we have a special volumetric flask called the volumetric flask. Its volume is very specified and specific. And so as long as, and if there is a marking near the neck, as soon as the liquid touches that marking, we know the volume is exact as stated on the volumetric flask. So now here, molarity is moles of solute per liter of solution. And therefore, we can, so when we say that 1 mole of NaCl divided by 1 liter will give you a 1 molar solution, and vice versa, you can convert it. So this is the standard unit of conversion that you have. You will get three possible steps, just like in density. 3 terms are there. You can solve for 3 terms. So moles divided by molarity will give you volume in liters. Then molarity times volume in liters will give you moles. And moles over liter is defined as molarity. A solute is usually in a solid form and is a soluble salt or soluble covalent compound. A solvent is considered to be a major component, and it's usually water that we use. And here are some methods of showing you how to prepare a solution of a known concentration. So first we weigh the sample, transfer it into a beaker, then add water, then we transfer it into the flask, rinse the beaker, and then continue to dilute up to the mark. The ion concentrations. Now, this is something very important, because later on, also in later chapters, when you come up to 102, you will have to have an idea how a water-soluble compound breaks down. So whenever you have a water-soluble salt, for example, CuCl2, it's written as AQ, but originally it was a solid. When you put it in water, it turns to AQ. In the formula CuCl2, there is one Cu and two Cl ions. So even though we write it as CuCl2, remember you cannot put it as Cl2. That means you have to break it down as ion Cl. This means that for every one copper, 2 ion in solution, there are 2 chloride ions in solution. So if we know the strength of the copper solution as 0.30, then the strength of copper ions will be 0.30, and for chlorine, it will be twice that amount. Now, if it was ion of the same type, FeCl3, then there is 3 Cl and 1 Fe. So whatever the concentration of FeCl3 is, for Cl, it will be thrice, and for Fe, it will be 1. This is another way to pipette a solution and make a dilution. So this is how to prepare a solution, just like we did before. But now what we are doing is we are having a stronger solution and we want to make it lighter or dilute or less strong. So dilute means we are diluting or reducing the strength of the solution by increasing the water amount content in the mixture that is there. So you transfer from a very high concentrated solution using a pipette, then transfer it into the larger graduated volumetric flask, and then go on adding. And you can clearly see that in the larger flask, the color of the solution is much lighter than that of the solution. So when we do dilutions by volume, the answer is the same. And it is a very, very simple concept that is there. When you add a solute and add water to it, the original amount, the strength of the original amount of solute remains the same. If you remember that, then the moles of solute at the beginning of the experiment and at the end of the experiment must remain the same. Therefore, we can use the expression molarity initial times volume initial must be equal to molarity final times mole final, which if your molarity times volume by definition is initial mole and molarity times volume at the end is final mole. And this expression is a very, very important expression to remember, because when we do the next slide, next unit, you will be using it for titration, and it all works on the same principle that is there. So when we have pH, this is another concept that you need to learn, because it depends upon the concentration of the H ion and OH ion. So if you want to measure the pH over a range of concentration, then the expression is pH is equal to negative logarithm to the base 10 of the hydrogen ion. P, the symbol P stands for negative logarithm to the base 10. Whatever else in front of P towards its right, you write. That is the ion whose concentration you are determining. So now if I write POH, that means I want the negative logarithm to the base 10 of the OH ion. Now, if I write Na, then I will need the concentration of the Na ion, and so on. But in general, pH plus POH is equal to 14. And that is the maximum that is there. So pH can be, in a simple direct format, this is what it is. So pH 1 is 10 raised to minus 1, pH 2 is 10 raised to 2, pH negative 3, 10 raised to minus 3 is pH 3, 10 raised to minus 4 is pH 4, and so on. So you can see. Now, if the pH of a solution is 1, then the pH plus POH is equal to 14. So therefore, POH is equal to 14, take away 1 is 13. And therefore, in that way, you can find out. So here it is the hydrogen ion concentration is 10 raised to minus 9. So pH will be 9 because negative of negative 9 is 9. So what is the hydrogen ion concentration of an acid that has a pH 7? No problem, because pH, the hydrogen ion concentration is 1 times 10 to the, whatever this number is, you raise it to minus 7. And these are the pH of different compounds or normally household items that we use at home. And you can see they are represented by their pH in order for you to understand what it is and how you use them and where you use them. So these are the worked examples. And so in solution stoichiometry, convert the volumes to moles of reactant to moles of products and grams of product, and vice versa. So you can do both ways the calculations. And with that, I'm going to stop sharing my slide.